各位老师、各位同学、各位朋友们，大家上午好。Good morning, everyone. Welcome to our multi-agent reinforcement learning session. 欢迎大家来到多智能体强化学习分论坛。We will totally have 4 speakers, and this morning we have 3, and the last one will be in the evening. The day after tomorrow. Well, this morning, our first speaker is Dr. Zhi Qiangpu. Dr. Zhi Qiangpu received his PhD degree in Control Theory and Control Engineering from Institute of Automation, Chinese Academy of Sciences, Beijing, China, in 2014. His research interests include nonlinear control, collective intelligence, and unmanned autonomous systems. He is currently an associate professor in CASIA and also the vice president of Taizhou Institute of Intelligence Manufacturing. Today his speak is about integrating knowledge-based and data-driven paradigms for collective intelligence decision-making, algorithms and experiments. 现在我们来一起观看朴志强博士的演讲。
Hey, ladies and gentlemen, good day. I am Pu Zhiqiang from Institute of Automation, Chinese Academy of Sciences. Today my topic is to address some of our attempts to integrate knowledge-based and data-driven paradigms for collective intelligence decision-making. I'll show some examples on our algorithm design and experiment practice. So I first give some background analysis on why should we combine these two paradigms, and then show how can we combine them through methods and practices. As we know, cognitive intelligence, or short for CI, has been a quite popular research area in these days. CI is a typical multidisciplinary topic, and different scholars or researchers may have totally different perspectives on it. So our perspective on CI is from artificial intelligence. As you know, China has proposed the concept of the new era of AI 2.0 since 2017, which consists of 5 most popular intelligence patterns, and CI is one of these 5 patterns. That means when we talk about CI, we are not talking about a specific method or system, but a general intelligence pattern. So this general intelligence pattern can be applied to many applications due to its networked, distributed, coordinated, self-organized, and resilient properties, such as the robots in the warehouse and logistics, the urban area vehicle risk security, or earthquake rescue, and so on. So due to its features of multidiscipline, as we discussed before, researchers have different perspectives on it. Here we summarize 5 of the most popular scopes, including biological swarm intelligence, internet-based crowd intelligence, and more agent learning and control, and population-based evolutionary game, and complex network. So it is quite interesting that different research community use different English words to describe these things. Here we cautiously use the collective intelligence to describe the common things among them. The challenges are quite obvious because, as a matter of fact, we even don't know how to coordinate hundreds of people, let alone man-machine coordination, and furthermore, purely unmanned system coordination. So there are three primary challenges. First, there are many theoretical blinds that are not clearly known. Second, we have limited knowledge or experiences in this area, especially in the systems embodied by physical pattern. In addition, we also lack enough high-quality data, which is quite different from the AlphaGo system or AlphaStar, where we at least have basic rules and large volume of online data. So current research roadmaps may be cased into two categories, the knowledge-based and data-driven. The knowledge-based paradigm includes domain knowledge user rules, experiences, or algorithms based on rigorous mathematical or physical models. The data-driven methods include machine learning such as deep learning, reinforcement learning, and diverse heuristic evolutionary methods such as PSO, AI. So each of these paradigms has its advantages and disadvantages. For example, the knowledge-based method is more expandable, but it may cost a lot for knowledge acquisition. And the data-driven provide a general solution, and it provides a continuous learning mechanism. However, it has poor explainability, and it needs large volume of data and computation resource support. So here are some examples. For example, the UAV formation performance under the war game are typically knowledge-based systems, while the AlphaStar agent in StarCraft 2 and the OpenAI5 agent in Dota are typical data-driven. So a later idea is, can we integrate these two paradigms together so that we can inherit both of their advantages? This is our basic motivation. So following this idea, next we'll give some specific algorithm design. So first, we have thoroughly summarized some of most potential methods that combine the knowledge-based and data-driven paradigms together. So we categorize them into a framework level and an algorithm level. The former claims that a proper framework is a container for complex problem, and specific K-based or data-driven or integrating algorithm can be put into this container. The later, the algorithm level, includes those algorithms that they inherently display the integration of knowledge and data. So details can be referred to this new paper that will be published in Acta Automatica Seneca soon. So first, we give a simple introduction on the framework level integration. The need for a hierarchical inference frameworks lies in at least two facts. One, for emergence of complex systems, regulations of the emergent behaviors cannot be easily solved. Next, for end-to-end learning, it shows quite no efficiency in complex tasks. So therefore, we need a proper framework to decompose a complex task into pieces. Here we show a conceptual hierarchical framework model based on the famous OODA loop. We decompose a complex task into 4 stages: observe, orient, decide, and act. And for each stage, it can be further divided into several modules. Then for each atomic algorithm module, we can choose to use K-based or D-driven method. So this framework takes the bottom-up emergence paradigm and the top-down planning paradigm together in a unified framework. And it also provides a learning framework that could solve the complexity of knowledge skill problems. Next, for the algorithm level, I'll give a detailed example on a multi-agent error coverage problem to show how to integrate knowledge and data together. And also will provide some of other algorithm design. So in many applications, we seek to coverage a specific error using a group of swarm or autonomous system, such as the earthquake rescue or the communication support system. So we abstract this problem as a multi-agent, multi-task problem. So here is the problem formulation. In a given environment, there are many targets. Here that are labeled as the black dots. And also we have some robots to cover these targets, labeled by the green dots. So each robot has limited coverage range and limited communication range. So our objective is to use minimum number of robots to cover the targets as much as possible, and meanwhile maintain the connectivity of all the robots. We also want the task to be completed as quickly as possible. So here is its mathematical model. So this item stands for the coverage rate, and here number 2 is the algebraic connectivity of a graph. So if lambda 2 is natural or equal to 0, we see the connectivity is satisfied. Also, this item, this equation, indicates the dynamics of each robot. So for this problem, we propose a knowledge-incorporated policy framework. It consists of 4 levels. The first 2 are data-driven, and the last 2 incorporate knowledge-based models. Specifically, at the first level, the OAR, or Observation Attention Representation, extracts the latent relation between the agent and the targets. The second level extracts the latent relations between the agent and its neighbors. The third level includes a knowledge-based model to guide the policy learning through reward design. The last level includes a knowledge-based model to filter the disconnectivity behavior and ensure that the proposed method can guarantee the connectivity. So this is the first level. Basically, we use the graph network and the attention mechanism to learn a latent relation between the agent and the targets. The second level, the interaction attention representation, is similar to the OAR. We learn a latent relation between the agent and its neighbors. So for the knowledge-guided policy learning, one of the major problems is how to maintain the connectivity of all these agents. As we know, for a topological graph, the second smallest eigenvalue, that is here the number 2 of the navigation matrix of the graph, stands for its connectivity. A larger eigenvalue means a stronger connection among the agents. So we compute this parameter number 2 and incorporate it into the reward design to guide the agent behavior. So based on the above learned policy, the multi-agent coverage with connectivity maintenance can be addressed to some extent. However, due to the probability characteristics of deep reinforcement learning, the connectivity of the robot network cannot be guaranteed. Therefore, a knowledge-nested policy filtering is further designed. Here we need another knowledge-based model, that is, for multi-robot, a system with initial connected communication topology. The connectivity is preserved if each robot I has a round step delta xi satisfying this condition. So here we design a critical error and a non-critical error. So if the robot interacts in the critical error, we design the run step like this. And if they interact in the non-critical error, we design its run step like this. So next we use these constraints to filter the policy produced by the reinforcement learning. Then we can guarantee that the policy finally obtained can guarantee the correctivity. So here is the simulation configuration. We use 5 robots to cover 10 targets. So each robot has the same configuration. To show the superiority, transfer is compared by performance metrics of reward, coverage rate, the number of disconnection, and coverage time. And we can find that the training curves of we call the KGP net, that is, we use the OAR, IR, and the KGPIR. The KGP net is superior to transfer. So furthermore, a quantitative comparison among transfer, KGP net, and KIPF, that is, we have the totally 4 levels. The comparison is conducted. So the performance of transfer is weaker than the other 2 methods. And KIPF has the best results, which has combined the advantage of KGPNet and the connectivity maintenance method. These 3 videos show the simulation results of 3 scenarios. We can see that the robots perform well in all the scenarios. They can cover the target and maintain the connectivity. So we also design a general experiment platform to validate our algorithms. The platform supports both UAVs and UGVs or robots. We incorporate many indoors and outdoor positioning and navigation devices and sensors together. Therefore, it can be an indoor system or work outdoor. So this is our indoor experiment. We use 5 UAVs to cover 10 UGVs, which serve as the dynamic targets. So it is noted that our algorithm work quite well. So this work has been published in Accra 2021 conference. So next, I quickly go through some of our other algorithms that display the K-based and D-driven integration ideas. The first will address a flexible formation maintenance and obstacle avoidance problem. Suppose we have a leader agent and a follower agent. They need to navigate to the corresponding destinations and maintain a specific formation. Also, there are some dynamic obstacles. So obstacle avoidance problem should also be considered. So here are our problem formulation. So we want to solve it in a deep reinforcement learning manner. So the idea is quite simple. We use a 2-stage learning scheme, including imitation learning and reinforcement learning, which is quite similar to the idea of AlphaGo. The difference is that in imitation stage, AlphaGo learns the human policy using available game records. However, in our problem, we have low human data. So we try to let the agent to learn from knowledge-based algorithms. Specifically, for the formation problem, we design a formation control protocol based on the concessions theory. And for the obstacle avoidance problem, we design an ORC algorithm. So then these 2 knowledge-based methods are used to generate demonstration data for the subsequent reinforcement learning. So this scheme could be a general idea. So here are some simulation and experiment results. The results has been published in IJT transactions on neural networks and learning systems. So next, we also attended the National Multi-Agent System Combined Challenge in the last year. So this is a much more complex problem, and it is not easy for pure knowledge-based or data-driven algorithm. We propose a comprehensive framework to integrate these two paradigms. Finally, we won the first prize in the heterogeneous group and the second prize in the homogeneous group among more than 20 teams, more than 200 teams. So furthermore, we also tested 50 knowledge-based agents combining with 50 data-driven agents. So here is a video. Here's the blue, the red are the knowledge-based agent, and the green are the data-driven agent. So it is quite interesting to notice that at first the knowledge-based agent dominates the situation. However, gradually the data-driven agents twisted the situation because of continuous learning. So this example may enlighten us on how to drive the agent evolution using knowledge and data together. And last, we have developed some physical platform for potential practical applications. So here are some of our platforms. Also, we developed the driving, the control, and the decision-making boards for algorithm integration convenience. Here are our indoor environment to conduct the experiment. As seen before, the system can also work outdoor. So here are some experiments. For example, this shows some agents cooperate in complex terrain. This shows some smart formation transformations with UAVs and UGVs. This shows a consensus-based protocol to validate in dynamic topology. So at last, we also develop a software. This software supports both virtual and actual agents. So this video shows how the virtual and the actual agents coordinate each other. So first we put any number of agents here, and we also put some targets in the environment. And then we send some agents to detect the targets, and at last, some of the agents are sent to cover these targets. Here, we see as the color, we have two actual vehicle UAVs. They work together with some of other virtual vehicles. So this software is expandable, it's open. So you can add any of other algorithms and agents into these systems. Okay, that's all of my report. Thanks for your attention.